This is Algebra 2 with Trig, the first day of Semester 2, Unit 4.1. We talk about the relationships between functions and their inverse. So we have a table, and we're going to observe these two different tables and see what's different about their inverse relation. So we're going to graph out the first table. Perhaps. There it is. So we graph those points of the first table. Now, if we plot this line that's called y equals x, we're going to talk about what's going to happen with these other points. What we're going to do, we did this in geometry class, we are going to reflect these points over y equals x. So we go diagonally. One diagonal till you get to the line of reflection. So we're going to go one diagonal past it, and that's going to be our new point. 1, 2, 3 diagonals to get to the line of reflection. 3 to get past it. So that's going to be our new point. And we can plot that other table. And you can see one way you can identify that location is to diagonally come across it. Or, from what you saw in your notes, the table, the x and the y are switched. -1 for the x, 1 for the y, 1 for the x, -1 for the y. 0, 3, 3, 0. Those are inverse relations. They are reflected over the line y equals x. Let's look at the second set of tables. If we plot out our first set of points, we're looking at those points. If we draw our line y equals x, you can find the other points by going diagonally to them. You could find the other points by just switching the order. This is over 2, up 8. We could go over 8 and up 2 is another way to have done that. So those are reflections over the line y equals x. And we can connect those dots. I don't think I did that on the other picture. And we can connect those dots. And now we have two functions that are inverses of each other. And we can come up to our last example that's in our notes. And we can plot the points. We can look at those connected points. We can reflect those over the line y equals x. We can plot those, the other table, and connect those. So these are two graphs that are considered inverse relations to each other. And in fact, these just aren't relations, these are functions. You know from Algebra 1 that a function passes a vertical line test. We'll talk more about that tomorrow. So what do we notice about these two tables? Somebody use their words. What do you notice? Observe the following pairs of tables which represent inverse relations. What do you notice?
On the second table, the y x values are split from the original table.
Exactly. The x and y values are switched. From our original, all the x's became all the y's of our inverse. And all the y's of the original became all the x's of the inverse. So an inverse relation is a reflection of the original relation. So if you're given these tables now, can you create the table that is the inverse of that? What are you going to do? What's going to make the inverse table? If this is the original table, what makes the inverse table? Well, we talked about switching the order. So 2, negative 3, 12, negative 1, 47, 0, negative 8, 2, negative 32, 7. We would expect all the y values became the x values, and all the x values became the y values. They were reflected over the line y equals x. The y values are the x values. And just doing it twice, 54 and 8, 22, negative 4, and you should be able to fill in these tables without purely copying off the screen. Where all the x values became the y values, and the y values became the x values. So if the x values become the y and the y become the x, how is that going to affect the domain and range? What's domain? What are the domain values? We know domain are the x values. So if you have a domain, these are the x values that exist in a particular function. They're going to become the y values. So they're going to become the range of the inverse. Simply, it is the same notation. If the x values are becoming y values, then the domain is going to become the range, because the range are the y values. So what used to be the y values, or the range, is now the domain. And the way we read this is a curved bracket tells us that it approaches this. We can never reach infinity. We can only approach infinity. Negative infinity just means that for the domain we're heading to the left. And then we come up to the x value that is 5, and it includes 5 because it's a square bracket. The square bracket means it includes the value. The rounded bracket tells us that it approaches the value. And always the smaller number goes first. So negative infinity, comma 5, 2, comma infinity. The smaller number's first every time. So here is some notation. Negative pi over 2 and pi over 2. Those words are totally new to you. You may have never seen this type of number before. This is terminology that we'll talk about with trigonometry. Pi over 2. It's just different. But once we learn what it means, we're okay. We're very used to numbers like -1 and 1. This is kind of like 3.14 divided by 2. 3.14 divided by 2. It's another way to think about that in terms of a number line. But all we're doing here is the domain values become the range, and the range is going to become the domain. In this case, they have square brackets. That just means if we were to draw out a picture, the y values would go from -1 up to 1 and stop. Now let's think about it with a graph. We have our function 3x minus 1. And that gives us this graph. That is our f of x. That's our original function. Our original function would create this table. There's an infinite number of points that could be put into a table. These are just some of the points that are put into the table. Now we're going to graph the inverse. We're going to reflect this over the line y equals x. Where are the points going to be? Okay, we're going to switch them. When we use the word opposite, we often think about that as positive, negative opposite. But switching is what opposite I think you're referring to.
Yeah.
So we're going to switch our x value, put the x value for the y, and put the y value for the x. Switch them all. So now we can come down and plot those. -7, -2. And you should be able to plot your own points without copying from me. -4, -1. -1, 0. Two, 1. And 5, 2. And the notation we use for the inverse is f -1. That stands for the inverse of the f function. So we're going to come down here to this equation. What type of shape do we expect this to be? This is a parabola. It's x squared. How do we do an x squared? Well, we know that an x squared, if we're just looking at x squared has a parent function at 0, 0, 1 over 1 up, 2 over 4 up, because it's 2 times 2 is 4, 3 times 3 is 9, and we have all the reflections across to make our U shape. That is what x squared is. -4 makes the graph come down 4. So if you notice here on the grid, we came down 4, and then we did our basic parabola. Over 1, up 1, To the left, negative 1 times negative 1 is 1. From the vertex, 2 over, 2 times 2 is 4. To the left, negative 2 times negative 2 is positive 4, so we go up 4. And you can see we're landing right on those spots. Over 3 would take us up to 9. Take us up 9 units. Not up to the 9, but up 9 units. Negative 3 is going to take us up 9 units. And that's where our table comes from. At negative 2, we're at 0. At negative 1, we're at negative 3. At 0, we're at negative 4. At 1, we're at negative 3. At 2, we're at 0. And we could also do the other points. It continues on. So you could go diagonally to figure out each of those points. Or you can just switch them. 0, negative 2. Negative 3, negative 1. Negative 4, 0. We're just switching the values, x and y, from the table. We've talked about multiple ways and how you could figure out where these dots come from. Some people even like to turn your paper so that the original x value is now your new y value. We're down here, over 1 up 1, over 2 up 4, over 3 up 9 would take us right to this location. And we could connect those dots. So lots of different ways for us to think about it. That's all an inverse is. F inverse of x. That's our inverse. Notice here, we're going to talk more about this tomorrow, this is not a function. When you do a vertical line test, for this value of x, we're getting 2 different y values. That's a topic we'll talk about tomorrow. That is not a function. So that's where the word relation comes from. This is an inverse relation. Where this one up here, it passes a vertical line test, so we could in fact call this one an inverse function. The dotted line on the graph above is y equals x. What do you notice about the graph of the inverse relation and the original in regards to y equals x? We've talked about it. What does the y equal x have to do with this process? The points are reflected over y equals x. So the graph of the inverse and the original function are reflected over our line of reflection. The graph of a function's inverse is created by reflecting the points of f of x over y equals x. Everything we've been talking about. You can either physically reflect it, that means count diagonally, or we can just switch the table. Many of you will just switch the table. but the whole process is reflecting over this line of y equals x. So now you take this equation, graph it, figure out the inverse, and graph that. You will most likely make tables, I would expect. Or you could plot this point, make your y equals x, and reflect it over it. And then try doing it with the parabola. Pause the video and go ahead and try that. So this is 2/3 x plus 6. We can come up to 6 and do our slope of up 2 over 3. Since I run off the grid, now I'm going to consider points that would come in to the second quadrant, which would be down 2, backwards 3. My slope is 2 over 3. I can put negatives in front of both. -2, -3. And I'm creating the other values for the equation. So this is f of x. So you can notice that this is at -6, +2, -3, +4, 0, 6, and 3, 8. Those are points that are creating your equation. Now we can take a look at f inverse of x. We could switch our points. The x's become the y's. And then you can simply plot those. +2, -6, +4, -3, +6, 0, and 8, 3. So that's another way that you could graph that out. I like to put in my line of y equals x. If you like to go diagonally, you'll see that those points will line up. Go diagonally, go diagonally. Those points will line up as we've talked before. Last one. Here's a parabola. I know that a parabola has the shape of 0, 0, 1 over, 1 up. From your vertex, 2 over, 2 times 2 is 4, so 4 up. That's what a parabola looks like. Well, we're going to stretch it vertically. We're going to make it go up twice as much. 2 times as much. Much more narrower. And we're going to drop it down 8. So a way we can do that is we can go down to 8 to begin with. 1, 2, 3, 4, 5, 6, 7, 8. We usually go over 1, up 1, but now we're going to go over 1, up 1 times 2. So we're going up twice as much, because it's 2x squared. Over 2, up 4 times 2. That means to do it twice. Twice as much, because of the 2x squared. And 3 would go up to 9, but you got to do it twice. So that is considerably higher. This is more narrow than the typical parent function. This is your f of x. And the points that we see for f of x, we have the point at -3, 10, -2, 0, -1, -6, 0, -8, 1, -6, 2, 0, and 3, 10. Because it was up 8 and then up 10 more to get to 18, which is 9 times 2. So we know our f inverse function is going to be the switch of those. 10, comma, -3. -2, 0. Or actually, that'd be 0, -2. -8, 0. One, -6. Oh, sorry, I said that backwards. I'm getting all confused now. -6, 1. 0, 2, and 10, 3. And we can connect those. That is your inverse function.